Welcome to another episode of 3-Minute Videos with Nathaniel. Today, we will now solve question 1G of MAT Oxford 2010. Before I begin, let me just say that this is the 93rd video that I've done of MAT. It is quite a really interesting one. And you know, we mathematicians are like chemists. We always find out the chemical formulas of these numbers. And you know what the chemical formulas are to us mathematicians? They are prime factorizations. So 93 is a number on the semi-prime, which means it is a form of two primes multiplied together. And 93 is the 28th distinct semi-prime. And you know why I say this? It's because 28 is a perfect number. It is the sum of its divisors. You don't believe me? 1 plus 2 plus 4, these are all divisors. 7 is a divisor, 14 is a divisor. And then, wow! What a perfect number! Other perfect numbers are 496, 8128, and I don't know why I memorized this, but it's 33550,336. Wow, this is the 5th perfect number, and I made an effort to memorize this. Okay, so this MAT question gives us a function. So what do we do? As with any other functions, we start at the beginning. 1, and then for the second term, we put it down here. 2, 4, and then we put the doubles 4, 8, and then we put doubles right after 4, 8, 8, 16. Then we have 8, 16, 16, 32, 16, 32, 32, 64. Well, this sequence reminds me of something called the Thue-Morse sequence. So you start with 0, and then you replace every 0 with 0, 1, and then you replace every 1 with 1, 0. This is a very interesting sequence. I think you should take the time to explore the Thue-Morse sequence while you can, while I work on this MAT question. Now, what is the term under 64? Well, F2n is 2 times Fn, so we write it down here. So because we're not counting the integers, rather we're just doing a procedure tree. And since these are greater than 8, we can safely say that there are no more terms greater than 16. So how many of the question actually states how many terms have the value 16? Well, let's count the 16 here. 1, 2, 3, 4, 5. Wow, 5. Well, there's one relation between this sequence and the Fibonacci sequence. So let's write down n. So 1, 2, 3, 4, 5, 6, 7. Now what's 2 to the power of n? These are the doubles that we met. 2, 4, 8, 16, 32, 64, 128. And this is the Fibonacci sequence, often named Fn. 1, 1, 2, 3, 5, 8, 13. Now, you see, Fn is actually what is called the counting function. How many terms are on the term 2 to the power of n? So that means that's called the counting function Cn. Let's count. So, Cn, where the n is actually 2 to the power of n, so we have 1, then 2's here, 2 4's, then 3, then 5, then whoa! It's the Fibonacci sequence right again. See, that's a very striking relationship when you start to observe sequences more. When you learn to observe sequences, you can actually see links between these new contrived sequences and well-known sequences like the Fibonacci and Lucas sequences. Other sequences that you may wish to explore are the center octagonal numbers, which are basically the odd squares. My personal favorite, the center hexagonal numbers, tetrahedral numbers, and pentatope numbers. And the simplest of them all, triangular numbers. They're probably the most basic figure-eight number sequence that ever exists, but they actually have a lot of mysteries hidden inside them. Why don't you try finding them out? Hint. One of them involves summing 3 triangular numbers at a time. Can you figure out what is it? Anyway, goodbye and see you in another MAT video!